Now that we've discussed functions, we're going to talk about pulmonary pressures. And so we've got 4 pressures that we're going to discuss here, 3 of which are actually occurring in the lungs, and 1 is kind of the outside environment and completely out of our control. And that first one is atmospheric pressure. So when we talk about atmospheric pressure, we're just talking about the pressure of the air. Whether or not you've thought about this or know this, air has weight. Okay, and so that weight exerts a pressure. The easiest way to understand that air has weight is go pick up a welding tank or an oxygen tank or something like that. Okay, there's weight in there. Or you could just even compare those little spray bottles that have like compressed air in there so you can clean out your keyboard. There's different weight between empty and full. All right, now at sea level, the weight of the atmosphere, or the pressure of the atmosphere, is 760 millimeters of mercury, or 1 atmosphere. Now, if you go to the top of Everest, it's about 1/3, okay, of the pressure. And the reason being is that the atmosphere, as you go higher up in the atmosphere, there's less air above it pushing down. Okay, so think about a pool. If you dive into a pool, the farther down you go, the farther that you dive, you can feel the pressure. It's greater weight. You have more water above you. Now, it's important to know that regardless of where you're at on the Earth, the composition of the air is the same. Okay, so even if you're on top of Everest, there's 79% nitrogen, almost 21% oxygen. Okay, what's changed is the pressure, so there's less air up there. So even though it's 21% oxygen or close to it, there's only about 1/3 as much air. So just to keep it simple, and this is not how this works, but you would have to breathe 3 times as much to get the same amount of oxygen into your bloodstream. All right. And so we can't change pressure of the atmosphere unless we change our altitude or elevation. So when I go to Utah this weekend, I'm going to go there and the pressure is about 20% less, I think is what it is. Okay, so here it's about 760, there it's about 600. All right, so it's still 21% oxygen. There's just less air. There's 20% less air. Now, the next pressure that I want to talk about is intraalveolar pressure, and that's just exactly what it says. It's the pressure of the air within, that's what intra means, inside the alveoli. Okay? Think of an alveoli as a balloon, okay? And really it's a great analogy, okay? A balloon is very similar to your alveoli. All right? It doesn't really like being filled up, but it's got that good recoil to kind of collapse. Now, if you take a breath of air out or in at the end of a normal inspiration, so when you stop breathing or when airflow stops, alveolar pressure equals atmospheric pressure. You've eliminated the gradient. If there was a gradient, air would be flowing. Okay, and depending on which way that gradient goes, that will determine whether or not air is going into or out of the lungs. So when we take a breath of air in, the alveoli stretch out. Okay, and this is due for a variety of reasons. But kind of the easiest way is I'm going to draw, here's your thoracic cavity. So you've just finished taking a breath of air out. Now you time to breathe in, and here's your diaphragm. It contracts and goes down. And so what happens is the pressure in your thoracic cavity is decreased because the volume in here is increased. There's an inverse relationship between pressure and volume. The nice thing is that the pressure inside your abdominal cavity increases and the volume, due to the volume decreasing. And since pressure has decreased relative to the outside environment, okay, so we're going to say that there's a higher than normal pressure out here. During inspiration, air will go into your lungs. Okay, now the reverse is true when you take a breath of air out. That diaphragm relaxes, goes back up into your thoracic cavity, which decreases the volume and increases the pressure. Okay, and so we can visualize this with this graph here. So as I take a breath of air in, the pressure decreases for a little bit and then starts to increase. Okay, and then during expiration, the pressure increases, so I'm forcing air or able to force air out of my lungs, but then it decreases. So why are these changes occurring? Well, this is very similar to the Wigger's diagram where during ejection we have pressure increasing and then decreasing even though the heart is contracting and air is leaving the entire time. Okay, and so during the first half of inspiration you've got a decreased intraalveolar pressure due in large part to that increase in volume. Okay, so that's causing the decrease. But during the second half of inspiration we're filling those alveoli up with air. That's increasing the recoil pressure in the alveoli, so that leads to an increase in pressure. It's like a balloon. The more that you fill up a balloon, the harder it is to add more air because there's greater recoil pressure. Now, during expiration, the exact opposite is true. Okay, we're decreasing thoracic cavity volume, so that's leading to an increased pressure inside the alveoli. Okay, but during the second half of expiration, because we've gotten rid of so much air and there's reduced volume inside the alveoli, we've reduced that recoil, so we have a reduction in alveolar pressure. So that's pressure number 2, intraalveolar. The third one is intrapleural pressure. Now, before we talk about intrapleural pressure, it's important to know what we mean by the pleural cavity. Okay, so you have the visceral pleura that cover the lungs, the parietal pleura that covers the rib cage or lines the rib cage or thoracic cavity, and those two are essentially connected, and there's a space in between the two that is very thin and it's filled with fluid. We call this the pleural space. Now, there's pressure inside that pleural space. Okay, and it's important to remember or to know that the lungs and the ribs want to do two very different things. Their natural tendencies are very different. Okay, the lungs want to recoil, see that here? And the chest wants to expand, okay? So it's got an elastic component that makes it want to expand, okay? Now, normally, the pressure between these two is below atmospheric, okay? And so oftentimes when you see people talking about or read textbooks about intrapleural pressure, you'll have a negative pressure. Okay, you can't actually have a negative pressure. It's just saying that it's lower than atmospheric pressure, okay? And so what happens is when we breathe in, and this is pleural pressure here, is pressure becomes more negative, or it decreases as we inspire and it increases as we expire. Well, why are these changes occurring? And I'm going to go over this in class. I'm going to try and explain this here on this video. We'll see how well I can do. Okay, so here is my intrapleural space, right? And so the ribs want to go this way, and the lungs want to go this way. Okay, now let's just say that at the end of a normal breath out, that I've got a pressure of -5. Okay, so I've got a pressure of 5 wanting to recoil, but the ribs have a pressure of 5 wanting to expand. At the end of a normal breath out, your lungs are in a happy spot. Okay, the forces between lungs and ribs are equal and opposite. So the intrapleural pressure we'll just say is 0. Okay, between the two. Now that's different than the number on here, so don't get caught up in that. But now I want you to think of what happens if we take a big breath in. So this is, I'm sorry, I think I might have said at the end of inspiration, this is the end of expiration. So end of expiration. Okay. We call this volume in our lungs functional residual or functional reserve capacity, which we'll talk about, I believe, on the next video. Okay, so I'm going to take a big breath of air in. Okay. So what happens now is the force of the ribs wanting to expand is reduced because they're going the way they want to go. And so we're just going to say this is +1. Okay, but now my lungs are really full. They don't like it. They want to recoil. And so now that force has really increased. Okay, instead of saying it's -5, we're just going to say it's we'll just say -19 because that's what I said. Okay, and so now we've got a force, the total force is -18. 1 plus -19 equals -18. We have a very strong force going this way. And essentially, the lungs are trying to rip away from the ribs. And so what happens is the volume in here increases, which leads to a decrease in pressure. Okay? The ribs, the rib side are in a happy place. The lung side are not. And so they're essentially trying to rip away from the wall. And so we get a negative pressure. As we breathe out, basically what happens is that these walls kind of smash into each other or start to get closer to each other. And so that pressure increases because we're reducing the volume inside. So another way to think about this is that during inspiration, the ribs expand. That's their natural tendency. Lungs want to recoil. The volume increases. And that allows our pressure to become more negative. During expiration, the opposite occurs. Rib cage goes to the resting state, so that increases their expansion force. The lungs aren't stretched out, so that reduces their recoil force, and so the volume between that space decreases. Pressure becomes less negative. Remember, intrapleural pressure is always negative because the pleural space is sealed. And so this leads to the question: if the lungs and the ribs weren't attached, what would happen to the lungs? And the answer is they're going to be small because they have a natural tendency to recoil. Remember, they're like a balloon. Okay? And this is due to a couple of things. One is the fact that the cells that make up alveoli are essentially elastic. Okay? They want to recoil. That's their normal thing. And then surface tension, which we'll talk about in a little bit, there's water, a thin layer of water inside your lungs that actually help with this recoil, and that's really important. This surface tension also causes the lungs to want to recoil. And we'll talk about that more in a couple videos. Now, every once in a while, this pleural space becomes compromised, or like a poked hole. Okay, this is what happens when you have a collapsed lung. Okay, and so you have what's called a pneumothorax. Now, this might not make sense right now. It should in class, but I want you to think about your lungs are like a rubber band that's wrapped around a set of tongs. Okay, so here are my tongs, just those tongs that are springy. I love mine at home when I cook, and you got the rubber band around here. Okay, the tongs want to spread out. The rubber band doesn't want it to, and so they kind of find this happy spot. All right, that's a beautiful drawing, I realize. So last we have transpulmonary pressure, and I just want to make you aware that it exists, but we're not going to go into very much detail about what's going on. Just know that it's the difference between alveolar and pleural pressure. During inspiration, it generally goes up a little bit. During expiration, it generally goes down a little bit. And with that, we're going to end our little video on pressures.